Okay. So good morning and happy Tuesday. Hope you all had a great weekend. How's everybody doing? Good? All right. Um, so it's funny. Um, I submitted a new course proposal. I won't really say what it is. Maybe one or two of you already know what it is. Should it be approved? Uh, Stuff will change in a good way, at least as far as the computer science program is concerned. So I remember when I was your age, I thought one day I would love to be a professor and only work 3 days a week for 2 hours a day. And then I became a professor as an industry. And I remember talking to one of my advisors, Rod Grippen at UMass Amherst, and saying, I had no idea professors do all this stuff outside of the classroom. Why didn't you tell me? And his response was, I didn't want to scare you away. So there's a lot of proverbial stuff that goes into the making of the sausage, the academic sausage. Um, so if you're thinking about being a professor, certainly happy to chat with you and encourage you to do that. The profession needs a lot of uh, new perspectives, especially young people coming up. So that being said, today the plan is to finish up on the information dealing with local search, and then we will pivot to adversarial search on Thursday. All right. But before we begin, the usual administrative bits. The reading has changed. Please make sure you're staying up on the reading. I mirror in my modules here in class stuff from the book to try to explain some gaps the book doesn't mention and hopefully tell a good story. True story, but good story about the material. Assessments, homework number one is due this evening for the undergrads and due tomorrow for the grad students. I might slide the one for the grad students. I have to check some stuff with the syllabus. Any questions about the homework? Yes, Chris.
The graphs, I read them like digitally. Is it
Mhm.
okay if I like have the little graph and then number the steps on the diagram?
Yeah, you can, as long as it's clear to me what you're doing, there's no one standard for how to do it, okay? Great. And I appreciate you doing digitally. If you do it by hand, you're welcome to do that, but I flunked hieroglyphics reading, so please write legibly and neatly for these old eyes. Yes, Robert.
A side question.
Uh-huh.
With Manhattan distance of heuristic.
Mhm.
Question C of that is this vessel is this is referring specifically to the heuristic we're using or just the concept of it?
To show that you understand what admissibility means by talking about the heuristic that you're using. Any other questions? Yes, Nikki.
Phrase. The first question, what is the new three times? It says compute P H and F for three regions.
Did you say that last part for something,
It's the first part of the A star question. Compute P H and F for three reach states. Are we supposed to just, is that saying we have to do the first three steps of the G star algorithm or is it?
Yes, so A star is going to pursue certain nodes. And so what are those nodes they pursue? Right? Does that make sense? All right.
So that's just the first three.
The first three choices that it makes. Any other questions? No? Grad students? No? Everyone good? Quiet? All right. Okay. So why don't we jump right in? So, of course, I have a book of thousands of these things. So to warm you up, I had a question for you. Why don't seagulls fly over bays? No? I mean, oh, okay. You have the same book, huh? Or maybe someone told you a lot of dad jokes too. All right, because then they'd be bagels. All right. Anyways, boom, boom. So the question of the day, we talked about local search. And for local search, it only knew two pieces of information. the current state where it is and the immediate successors. And it can, therefore, because of this seemingly myopic view of the environment, and I'm going to stay closer to the laptop so it picks up the sound. I didn't charge the headset this last night. Because of this myopic view, it could certainly proceed through the same set of states again and again and again and again. And so with this, can we guarantee, my question to you, can we guarantee finding the goal? Can we always guarantee that? Chris? Mhm. Ah, and that's an important point that Chris makes, this idea of accessible, right? Because all you see is immediately what's in front of you. Okay, so let's continue on this idea. Chris mentioned accessibility. Can we improve on our ability to find the goal, given this myopic view, this notion of accessibility? Can we? How do you know if it's accessible? Because all you know is you try again and again, and you can't seem to get there. But can we improve on this? Is there something else that our agent might need to know or have? Have you thought about that? Chris? The amount of no's. And what would you do with this amount of no's? What do you think you would try? Let's just hear some brainstorms. You need to track something about the amount of no's. What about the amount of no's? Anybody? Tenzin? Okay. And what would you do with that piece of information? Mhm. So if it gets too big, you're going to do something else, right? Or maybe if you keep repeating something, I've seen this before, you're going to do something else. Okay. All right. So this idea then is about adding some other piece of information. And that other piece of information should help you try to decide things like, is it accessible? Have I been there before? Is this taking too long? And then perhaps use this information, a memory of sorts, to influence the actions that you take, regardless of the selection criteria in place, when you expand the frontier and pursue one of the nodes that you've encountered. Okay? Any questions? That makes sense? All right. And so when you go to continuous environments, things change. And the example in the book goes back to the Romanian vacation. And in the continuous case, the example problem they give, and that monitor's off. Usually with those monitors behind you, I don't have to go back to the laptop because I can see it up there. But this time, the left-hand monitor's off. You're going to place 3 airports. And the goal then is to have those airports placed in a way that it minimizes the distance between each city and one of the 3 airports. Okay. And so this is a continuous space problem because geographic location is continuous. And so in this, we place 3 airports. The first airport located at coordinate x1, y1 in this example, the second one at x2, y2, and the third one at x3, y3. Okay. So if our problem is then to search for a solution, we want a solution that has the property that the distance between each of these airports and this notion of the closest city is going to be the smallest. And so absolutely, you could come up with a function that tests, have I reached the goal? And in that case, am I at the goal says, what is the smallest way to arrange this configuration? Any questions? No? All right. And so you need a representation. And in this case, we're going to pose a six vector. Now, in this notation, the bold lowercase is going to mean a vector. And it's a tuple deliberately because the order is going to matter. And so we're going to concatenate together the XY coordinates of the first airport, the second airport, and the third airport together. And this is going to be our representation. So anytime we talk about a configuration, i.e. our state space, it's going to be an instantiation of the six vector representing a placement of the three airports collectively. Does that make sense? Any questions? No? All right. And so we need an objective. We talked about this notion of hill climbing, and we need something to use as the basis of a score that tells us whether or not a particular solution or successor rather is better or worse so that we can pursue that particular solution from where we are. So we have some function over our six vector, and this function is as follows. And so let's define a big C sub I. It's going to be a set. And inside of that set are all the cities that are closest to that ith airport. And so in this notation, I is going to index over the airport. So I can be 1 for the first airport, can be 2 for the second airport, can be 3 for the third airport. And so for each of the CI, we're going to have some number of cities, and each city is represented as little c, so little c element of big CI, and we're just going to take the sum squared differences of the x component to the x component of that ith airport, and the y component and the y component of the city to the y component of that ith airport. Does that make sense? Any questions? No? So this is our objective function, and you could certainly plot this objective function. Well, not really, because it's more than two dimensions. But certainly you could imagine this objective function being evaluated for all of the infinitely many instantiations you can have of the six vector. Then, if you could represent said objective function, you could perform hill climbing or gradient descent and find an optimal solution, okay? But again, here we're talking about local search. What's only accessible to you is the current state or instantiation of the six vector and the immediate neighbors arrived upon through some notion of successor. So let me ask you, given some instantiation of this six vector, it's continuous, it's real value. What is a successor? Let me ask the question of you. What is a successor? Can a successor exist? Chris?
I maybe guess that in this context, the successor would just be any like permutation of the vector other than the current one.
I see. So something other than the current one. If you are at some value, absolutely, it's some other one. How do you choose a successor? It's a hard problem because it's continuous. How many successors are there for a real value? Chris? It's infinite. Okay, so we have to do something else about this, and that something else can be one of very many different things, right? Okay, so we have this objective, and one of the observations that we're going to make is that this quantity holds true in a notional neighborhood around a particular instantiation of our six vector. If you don't move the airport very far, the cities that are closest, and therefore the sum squared distances along X and Y, don't change too much. Okay, so you have a little bit of wiggle room. You might consider this local neighborhood to be effectively the same state. Okay. If you stray too far away from the local neighborhood for some definition of far, so if you change X a little too much, change Y a little too much for airport one, two, and three, um, you're going to break this because eventually you stray away far enough that a city that was closest to that airport is no longer closest to that airport. Does that make sense? So one of the ideas about choosing a successor, not the only idea, one of the ideas is that maybe you look at changes in this six vector that are meaningful. Maybe these changes have to be big enough to matter in this representation, and perhaps that is your notion of a successor. But it's a hard problem because from a practical sense, this space is infinite. It's uncountably infinite. And because of that, well, it's a big problem. If you make your grain size, so to speak, of how far away you stray in calculating or considering what is a successor, if it's too small, your complexity blows up. If it's too big, your accuracy is not very good. So it's one of these engineering trade-offs, depending on the problem, you have to use balance those two concerns. So it breaks away as you stray. And let's imagine we have some association of cities with the closest airport. I just drew it this way, the bigger purple contour lines. If you move an airport, these associations may change. So you're searching for two things effectively. When you move the airports, you're looking at how big my successor should be away from the current instantiation, but you're also indirectly deciding what are the associations between cities and the airports. Does that make sense? All right. And so let's look at some strategies how we might do this. And the problem arises from this notion of successors being continuous. There are infinitely many ways you can say, move this point in a real valued space. Okay. And so one thing you could do is you could discretize things. You can chop up your representation into cells, and you decide how big these cells are. And in doing so, when you think about locations, you might be thinking about the center of a cell and not arbitrarily any position in space. Well, that's kind of nice. And then you have to weigh that trade-off about how many tessellations you should have, because that's going to impact your complexity. And again, how big they should be, because that's going to impact a notion of accuracy. So this reduces the state space, but you have to balance that trade-off between complexity and specificity. Does that make sense? Any questions? No? All right. With this, then, when you talk about successor, you're just adding some delta, which is the grain size or the cell size, to move from one cell to the next. And when you move from one cell to the next, what you're counting is a centroid of that cell. Okay. So if you tessellated this 20 by 20, that's a different complexity from this tessellation 3 by 3. So you control the complexity. And then based on what computational resources you have, you just make a choice and then go forward with that. Okay. You could also discretize by sampling. Maybe you choose some delta, and that delta is sized relative to what matters from what we alluded to earlier with this idea of big enough to make a difference in how the cities are associated. So delta could correspond to 1,000 feet, could boil down to a mile or a couple miles. You decide. So then you randomly sample in arbitrary directions some delta from where you are in your state space, that position, that six vector, and then you pursue one of them, evaluating the local so-called empirical gradient. And so you randomly sample, and in this case, you control how many samples you're going to take, and you control the suite of directions in which you're going to sample. So if you had, for example, every 5 degrees about the unit circle from where you are in space, that's different from every 15 degrees, some delta out in distance. Does that make sense? Any questions? So again, sort of where the rubber meets the road proverbially, you decide, and there's a cost, and you have to weigh that cost against what the quality of solution is that you're seeking to get. That makes sense? Any questions? No? All right. So let's look at some solving techniques. Sometimes, if your objective is in a functional form, and I'll add that's smooth and differentiable, you can solve it directly, which is kind of nice. Use mathematics instead of this empirical gradient deal. And so in that case, you take the gradient and you'd set that gradient to 0 and just solve in closed form, which is the ideal case, which is also why when you design objectives, it's nice to use families of functions that are already known. But in many problems, you don't really have access to families of functions to describe things. You're just doing things like discretization and empirical hill climbing. Okay. Any questions? And so this gradient is just the derivative of this objective function along particular axes over which this thing is expressed. And so, have you ever had calculus? No, well, you had 2. They don't do that in 2, right? That's 3. All right. And so if we had a function, and I'll just kind of demonstrate what that is in 2 dimensions. This is where my artwork fails me. So let's say this is the x1 axis, and let's say we have the x2 axis, and then let's say we have our function here, f of x1, x2. Okay, so if your function looked like a sheet, and let me just draw in some contour lines on this sheet. When you want to describe how this function changes along this direction, let me ask you, how does the function behave along the x1 direction? What does the function do if I only look at what happens in this direction, only that direction? Alexander? It decreases. So it decreases, becomes more negative. What about this direction? What does that function do in the x2 direction? So let's see. Let me draw something to make it easier to see. So if I were to scan here, if I were to scan here, if I were to scan here, what does that function do in the x2 direction? What are your thoughts? Alexander? It doesn't do anything. So it decreases to negative gradient in the x1 direction, and it's 0 in the x2 direction. So taken collectively, what the gradient does, it measures the slope or the rate of change, first order rate of change of a function, multivariate function, along different axes of measurement. Does that make sense? And so in many continuous problems, it's going to be vector valued. And if you have a functional form, this is immensely useful because it saves you a lot of computation. Once you know the gradient, you just plug into this function and you get your values and use that to select successors. Does that make sense? Okay. And so if you can't solve it in closed form, sometimes you can make local steps along this function. You can increment, in this example, if I only incremented the x1 value, or I only incremented the y1 value, or x2 or y2, singular values. And so with this so-called coordinate descent, you might not be able to solve this function in closed form, but effectively, whether empirically or mathematically, sometimes you can say, let me see how it changes just in one of these variables in my sixth vector in this example. Now, this is called coordinate descent, but there's a generalization, which I won't talk about, called projection pursuit, where you are calculating the direction in which you're going to take your step. Okay? Any questions? No questions? All right. And so another method they talk about in the book, and I'm going to fill in where the book doesn't give you the details, is Newton's method. Well, Newton-Raphson is the formal name. And Newton's method is a powerful yet simple solving technique for finding the so-called roots of a function. Now, please humor me. I'll tell you why this matters for something like landscape and hill climbing or gradient descent. And so what does it mean to find the roots of a function? Okay. So here we have a function, f of x, and I'm drawing a one-dimensional function of arity 1 just because it's easy to talk about. I don't want to introduce the multivariate case, at least not just yet. And so we have some function, and this is the root. It's where the function crosses the x-axis. It's where the y value, output of this function, is exactly 0. And so this is immensely useful for a large number of problems, specifically one of which is our interest, is to find the minimum or the maximum of a function. But we'll get to that in a couple of slides. And so here we start out and we make an initial guess. We just guess a value. And we're going to call that value x sub n, okay? After we guess that value, we're going to consider the tangent line on this function at xn. Okay? Now, let me ask you, can I compute this tangent line? Well, we wouldn't be here, right? I wouldn't be saying this if we couldn't. I guess I can. So we know the slope of the tangent line at xn. We just take the first derivative of f prime, and we evaluate that derivative for that initial guess, xn. And that's exactly the slope of this tangent line of f evaluated at xn. Does that make sense? Any questions? No? All right. So now, knowing that slope, one of the things I'll direct your attention to is where this tangent line pierces the x-axis. This tangent line pierces the x-axis at a value. We're going to give this value a name. We're going to call it xn plus 1. And you'll notice xn plus 1 is closer to the root, the 0, so to speak, of f of x than the original guess was. And if you think about why this happens, if our function is increasing and we draw a tangent line, that tangent line is going to point backwards towards the root. If our function is decreasing, gross level, that tangent line is going to point forward. And that pointing forward is towards the root of that function, because by definition of a decreasing function, if it's going to pierce the x-axis, it's going to do so going to the right. Does that make sense? Okay. So this xn plus 1, where the tangent line pierces the x-axis, is going to be an improvement over our initial guess, xn, an improvement on what the root is for this function. So now we want to calculate a formula for xn plus 1. But we need some other pieces of information. I argue that we have these pieces of information. Okay. Well, what do we know about this configuration? Let me ask all of you the question. Put yourself out there. Here are the thoughts. What do we know so far? Well, we have xn. Okay. We have the slope of the tangent line. Okay. We want to compute a function for xn plus 1? Any ideas? No? Yes, Luke. Point slope. Yes, absolutely. So if we know xn and we know our function f of x, we can calculate yn, that output of our function evaluated at xn. So we have xn, we evaluate f of xn, let's call that yn. And so with these pieces of information, armed with the point slope formula for the equation of a line, we can just plug in and arrive upon a formula for this xn plus 1. Okay, so let's go ahead and recall the point slope formula. So we have the slope m of a line, and we have a point, we'll call it x1, y1, and that point has to be on the line. And we have our point slope formula, y minus y1 is equal to m times quantity x minus x1, okay? So our slope, m, is just going to be the slope of the tangent line. We can calculate that. It's just the first derivative of our function evaluated at xn. And our point, well, we have our xn and our yn, okay? Xn comma yn is that point on the line. So we have all the components we need for the point slope formula. Okay, so with that, we have y minus yn is equal to f prime of xn times quantity x minus xn. And that's just plugging in what we know about this configuration into the definition for the point slope form. Any questions? No? All right. So we know that for x is equal to xn plus 1, that's the point where the tangent line pierces the plane. The corresponding y value is going to be 0 because where you pierce the x-axis, the y value has to be 0. Okay, so we take our point slope formula equation and we're going to plug in. Okay, so where we see y sub n, we're going to plug in f of xn. For the slope m, we're going to plug in our evaluation of the first derivative. And for that quantity, x minus xn, we have xn plus 1 minus xn. Okay. So we do a little algebra. We isolate xn plus 1. Xn plus 1 is xn minus the ratio f of xn upon f prime of xn. And so this recurrence relation is the Newton's method. And this xn plus 1, if we iterate over it, eventually we'll converge onto the roots of our function f of x. Does that make sense? Now, any questions? And again, I'm only showing it for the one-dimensional function. Nikki. Yeah.
Yes.
Mhm. It can't be too far away, right? I can post something on the Slack channel because it's beyond the scope of what I wanted to talk about for this class. But yeah, there's some guidance and some heuristics for how you choose your initial guess. Okay. Any other questions? No? All right. So you iterate this recurrence until you reach convergence, and your guess can't be too far from the actual root. Now, certainly, you know, if your root was like at 5 and you said, you know, 10 billion, right? That's far off, right? And it also depends in part on the complexity of your function, right? So there are a lot of situation context dependent things that you have to take into consideration. But in this class, you just can't guess too far away from the actual root, okay? And so now this is connecting this to this idea of gradient descent or hill climbing. Now consider your function. It can be any function. And I did set that one qualifier smooth and differentiable because Newton's method traffics in derivatives. If it's not differentiable, then you can't participate in Newton's method because you won't get to the recurrence relation. So if your function f of n can be any function, well, the first derivative is a function. And if you find the root of a first derivative, that's nothing more than the min or the max finding. And so if you traffic in first derivative, you can use Newton's method on that function to give you the optimal solution through Newton's method. Does that make sense? Any questions? No? All right. And so in this case, I don't know why I put this slide. We have this solution, and this is in matrix vector form. And again, here we have bold X, and it says the new version of X vector is the old version of X vector minus this gradient f of X. So that's the derivative along every axis. So that takes the role of the numerator here in the 1D case. And then here we have this HF. That's called the Hessian matrix. And the Hessian is the matrix of second derivative, partial derivatives in all of the directions. And so just like the 1D case, instead of xn, we have the vector x. Instead of f of x, we have the derivative, first derivative, the gradient of x. And then the denominator, we take the derivative of that function. That's the second derivative. The second derivative is the derivative of the first derivative, okay? And we have the same expression, okay? Only in this case, it's in the multivariate version. Does that make sense? Okay. And so with Newton-Raphson, by plugging in the derivative as your f of x, you can now find the min or the max solution from an initial guess. And in this case, your initial guess is going to be a vector valued initial guess. Does that make sense? All right. So I thought I'd fill all of that background in from the book. Newton-Raphson is very well known. There are lots of sources out there that cover it. But I thought I'd fill that in based on the brief mention only that the book makes. All right. Any questions? No? All right. And so there are a lot of other alternatives for finding maxima and minima in objective functions. You could use linear programming, a family of approaches called convex optimization, all sorts of things, stochastic gradient descent, all sorts of things. But this is just to say, if you have an objective function, there are many solution approaches out there of which you can avail yourself to try to find this notion of a minimum direction. Does that make sense? Any questions? No? All right. And so let's take a look at so-called online learning. Online learning is a type of local search. And this is a picture from Uber. And what you see in this is a cutaway scene of driving in autonomous self-driving car. In the upper left-hand inset, you see a live video feed. And the other picture down below is a list of the percepts that it's extracting from the environment. You see obstacles, and some of those obstacles are fixed, and some of those obstacles are dynamic, they're moving. And so in this particular case, in this type of learning, computation and your action is interleaved. You take an action, you observe the environment. You take an action, you observe the environment. And in this environment, it's dynamic. Things are happening while you're computing. The environment changes underneath you as you deliberate. And so with this, and this is a different picture at a stop sign, all of the percepts, and you see dynamic objects and you see static objects, the world changes. Now, when you're learning online, yeah, you can use local search, but there's a penalty for taking too long to deliberate, thinking too much. The world model becomes obsolete. If you were crossing, Main Street, I call the crosswalk of doom in front of the ASEC building, and you look to the left, look to the right, then close your eyes, memorize what you saw. If you waited 10 seconds, 30 seconds, the world would change underneath you. What you measured when you looked left and right doesn't hold true just even 10 to 30 seconds later. And so this is a problem. You always have to update your understanding of the state of the environment as you compute, And in this case, the longer you take, the worse it gets. And so when you do online learning, it can be effective for some types of environment, for non-deterministic types of environment. But in dealing with those environments, you have to evaluate contingencies. Well, if you drive, you've done this before. I'm driving down Main South. I'm on the main thoroughfare. I see a car come off of a side street. I have to think, what if that person doesn't stop, which they should do? What am I going to do? You have to evaluate alternative pathways through the state space as you interact. And so mapping and navigation is a good example for online learning. Essentially, you have to experience outcomes. And from that collective experience, you need some sort of memory. And you're going to use what you record in that memory as you interact with the environment to influence the decisions you make. Because legal driving says you have the right of way on the main thoroughfare. But driving on Main South doesn't agree with that. So you have to evaluate contingencies. But once I get off Main South, it kind of returns back to what legal driving should be in most cases. All right, not to disparage Main South, but it freaked me out the first 2 months it started with the club. So, but nonetheless, I digress. Okay. And so in the simple case, you have a bunch of pieces of information. You have the actions that are legal in every state, and not all actions are doable in every state. You need to know the cost of applying an action, and you have to know what that current state through that action transitions to. You have to build up these things. You need some goal test, some evaluation, and that goal can be multiple folds, not just coinciding with a particular state. And you're going to interleave your computation, your sensing, and your action. You have limited knowledge. You only know what's happening at the moment. So it's a local search, but also there might be things over time in the environment that you have to uncover. You can't just have it completely modeled until you experience it. And so you don't know what the result is from a state applying an action until you perform it. Even in driving, right? Just because you push the accelerator, it doesn't mean the car is going to move in real world in a particular way, right? You could have slippery conditions. It's going to change. You could have dry conditions. It's going to change. Okay, so you don't know what the result is of an action until you actually experience it. You try it, and then you see where the environment puts you. You have to get that percept and then impute the state from that, the resultant state. And you build that up over time. So the example that they use in the book is a simple example, but it still illustrates the point. And it's a maze world. And you can think of a maze world in something like self-driving cars as just a map of, maybe a map from downtown Worcester. I don't know if they call it that, near the Hanover Theater, to get to here, Clark, one of the parking lots. You have a precise map. You know where you are geographically, but you don't know where the obstacles are. You don't know what's parked. You don't know if the turn lane is prohibited because there's a big snowbank in the winter. You don't know what pedestrians are going to be walking there. And so you have complete ignorance of the environment. And it's not until you start acting in the world, getting the next set of percepts, that you can start to build up what state means. And so in this example, we have S in position 1, 1 in this simple maze world. And we have the goal G in position 3, 3. Now, unknown to you are these obstacles, these red walls. You didn't know that there's going to be a school bus stopping at a particular time. I just this morning saw someone run the school bus line to stop. That's a pet peeve because they're little kids, like little kids crossing the street. But anyways, so in this world, the agent has to discover that when you execute the up action, it brings you from 1, 2, 1, 1 rather, to 1, 2. Maybe, depending on conditions, it might not bring you to 1, 2. It might bring you somewhere else. Maybe there's a patch of ice and you slip and you end up going sideways, right? Perish the thought. But nonetheless, the agent doesn't even know how the world behaves when you act with it until you try it. And it also doesn't know that when you execute the down action from 1, 2, that it brings you back to 1, 1. You have to discover that. You have to discover how you move through the world. So you have to build an understanding of the dynamics, how the world behaves as you act within it. Moreover, you have to uncover the obstacles in the world. Now, it's as simple because it's an example that I drew some fixed obstacles, but there are cases where the obstacles aren't fixed. They move, right? Someone pulls out of a parking space. That's a dynamic obstacle. You have to update your understanding of what happens in the world. Driving in, there's a car parked. Driving out, the car's not there anymore, right? It's a dynamic obstacle. So you only have partial knowledge. You can know your actions, what's admissible, but you don't know the obstacles. You have to build in your map some representation of things you can do, things you can't do, and things like obstacles. Does that make sense? Any questions? No. And so the idea of what a goal is, you can have different types of goals. Maybe you want to reach a particular location. You want to get to the parking lot here at Clark near the geography building. Or you might just want to explore the environment to gain more experience about how the environment behaves. In that case, you're going to select actions that reveal new information, right? Just for the purpose of understanding the environment. There's another concept in the book called competitive ratio. If you knew the environment, how is your path off relative to what optimal is in the known environment? If you knew all of the environment. And so the closer to 1, the better you are. And when you explore, you might run into a dead end. You might reach some pathological case in the environment where your actions won't allow you to escape that particular state, an absorbing state in your state space. Does that make sense? So any questions? So there are a lot of things that can go wrong, right? Dynamic environments, continuous search spaces are messy and hard. So one of the things that can occur, I alluded to before, you can reach a so-called dead end. And a dead end, you can think of as an absorbing state. You navigate to it, and for whatever reason, you can't navigate away from it. And so in one case, we see this state space here. You transition from a start state to A, and you pursue the bottom path, and then you arrive to this node, and you can take an action, but let's say that action puts you right back into that state. You're stuck, right? These dead ends can confound these online searches. They're there in many cases. And so in some models, it's thought of as an adversary, and that adversary can place roadblocks. I'm driving up Main South. I get near the Hyatt Middle School. There's a car right behind me. There's a car in the other direction beside me. School bus stops. Lights go on. I'm stuck until all of the kids get off that bus, right? That's a dead end. Okay. In another type of pathology, in this case, we start here at our start state. We want to get there, but the roadblocks or the walls or the mazes or something about the environment gives me this circuitous path. Practice that word, never say that, circuitous path through the environment. Now, how horrible would that be if after navigating through these mazes and catacombs, all of a sudden there was a dead end right there? You can see the goal, right? The only alternative you have is you have to backtrack. But backtracking means that your actions are so-called reversible. You can kind of undo the result of taking an action. And that's not always the case in the real world, right? I can't undo being stuck behind that bus. I've reached a dead end. And so one of the characterizations of state spaces, particularly online learning, online search, and local search, is your state space safely explorable? Can you reach the goal state eventually from every state in your state space. Now, if that's not the case, well, hopefully your action set is reversible. Things like the 8 puzzle. You can move the space in one direction. Oops, I didn't like where that led. I can move the space back. Those are reversible. Going through a maze, you take one step along this hallway. I didn't like that, where it's going. I can take step backwards. But not all actions are reversible, right? So you have to exercise care when you are presented with a problem and you're going to do online search. Okay, but in this, there's no guarantee that your costs are going to be bounded. Because you might find, I go forward, you know that song, 1 step forward, 2 steps back. You might be doing that quite a bit in some environments, and that's just only going to add to your path cost. Does that make sense? So yeah, online learning is messy. Online search is messy. You have to look at the problem. Sometimes it means in practical sense, in case of robotics, adding sensors or changing the way the mechanism navigates through its environment. Okay. And so one of the ideas that we said at the outset, sort of alluded to it, you have to add something. And the something is a type of memory. And as you experience the world, you're collecting pieces of information about the environment that you uncover through experience. So for example, you move to a new area. You don't know the roadways. You know, some routes are more pleasant than others. Some routes are more trafficy than others. You know, at rush hour, I'm going to take this route instead of that route because the lights help the traffic go along, and so forth. So systematic search, what we've done, like breadth first search, depth first search, A-star search, it explores the environment entirely offline. Now, in this case, for online search, it's a type of local search, so you don't have the luxury of a complete definition of the state space. You have to uncover it as you move through it. So you take an action, you receive a percept from the environment. From that percept of the environment, you calculate some notion of state, you estimate it, and then you update a map of the environment. So then when you take your next action, you're using all of these pieces of information you deposited in your memory, your map, to influence what action you're going to take next. Sometimes you take actions just for the purpose of exploring the environment. Let me drive down this street and see where it goes. In fact, I discovered, what's it called? What intersects with Hawthorne? Is it Maywood or H something? I can't remember. I discovered a new route to get here. I'm pretty proud of that. But anyways, sometimes you take actions just to uncover pieces of information about the environment. And that's okay, because the more you know about the state space, the better the decision can be, and I say can, not will be, the better the decision can be when trying to select future actions. Any questions? So your successor function is only limited to the present state, and you want to avoid wandering all over the place very, very far. Because if you have to reverse your actions, you're going to be backtracking quite a bit. If I were driving forgot the name of the town in Oregon. If I were going to drive to Oregon, I don't want to end up in Miami only to backtrack, right? I want to make sure I'm kind of trying to progress in that direction westerly, but I don't want to stray too far, either northerly or southerly, to only have to backtrack, right? That will blow up my complexity of time. So you want to avoid traveling to distant states, and you want to kind of be relatively local. Something like a depth first search will do that, but not exactly depth first search. So when you do online, exploration is good, but you don't want to overdo it all over the place, because in real terms, that's going to cost you time and it's going to cost you space. Any questions? No? So this is in the book, and this is online DFS agent. And essentially what it does is it populates a data structure called results, and results SA tells you how the environment behaves. It says what state S prime do you wind up in if you take action A in state S. And so you start out first checking to see if your successor is the goal. Well, that's the ideal. The first try you make, you're at your goal. And if it's new, then you have or maintain a list of states you haven't tried. And in this, the goal is to try every action in every state. And you track all of that. Because if you try every action in every state, as you build this results data structure, you'll converge with enough moves upon a complete understanding of how the environment behaves. And then subsequently, you can use that understanding to take better actions, more informed actions. Okay? All right. So if we have in real state, we populate the results matrix. So we talk about the result of getting to S prime from S through action A. And then we add S, the predecessor of S prime, to a data structure called unbacktracked. And so if you find that an exploration is selecting in depth of trying all the actions for all the successors in depth, if it's not fruitful, you want to be able to pop your way back to backtrack ultimately to the predecessors to then try all the actions in other successors and filling in this results data structure. Does that make sense? Okay. And so you add S to the unbacktracked list. And if you have not tried S prime's actions, all of them, then you're going to go ahead and try more of the actions, these actions B. And so you talk about this unbacktrack allows you to pop back to explore more things. And then you have an untried list. And this untried list gives you all the states whose actions you haven't exhausted. And once you've exhausted all those actions for that state, you've done everything or learned everything you can about that part of the state space, and then you go someplace else. Does that make sense? All right. So you try each action in every state, and then you set up the backtracking so you can walk your way back up and explore all the actions in another successor. All right. And this terminates when the backtracks are depleted. And this only works with reversible actions. Because in the physical world, when you do an online search, in order to get back to that predecessor, you have to reverse those actions. If you went down and you want to get to the predecessor, you have to go up, for example. Does that make sense? Any questions? No. All right. Hill climbing search is a type of online learning, and it can get, as we discussed, stuck in local maxima. And so random restart in online learning, online search, is not possible, right? You can't just quantum connect yourself to some other location. That's not what happens in online environments. If you're in autonomous driving, you can't just say, what happens if I'm in Boston and I want to drive a train? You can't do that because the most you can do is explore relative to where you are right now here in Worcester. And so random restart is not possible for online environments, but you can explore the environment with a random walk. And if you do this random walk and that goal is reachable, eventually you will reach the goal or you complete all of your exploration. And so this example in the book of random walk talks about one of the pathologies of random walk. And what they said is that in this case, you're going to make a lot of left to right oscillations. And the reason for that is that the number of edges that go left to right is twice the number of edges that either go diagonally down or diagonally up, right? So if you're going to make a random selection of an action to pursue, more of the time, you're going to be going left and right. So that means you're going to produce a lot of repeated sequences. It's going to increase the amount of time that you spend. But one solution is to have a notion of a memory. And that memory, H of S, is indexed by each one of the states in your state space, and it stores an estimated cost to the goal. And the example they give is as follows. Now, this may produce some oscillation, but what you're doing is using the accumulated estimates of cost to the goal to influence subsequent decisions. So we'll start in frame A, and let's imagine we're in this, is that pink or red? That red state, and it has an estimated cost of 2. Now you could either go to the left or go to the right. And if you go to the left, well, that's a cost of 1 for that step cost. And then we see that the estimated cost of the goal is 9. 9 plus 1 is 10. If we were to go to the right, well, that's a step cost of 1, and the estimated cost to the goal of that state to the right is going to be 2. 1 plus 2 is 3. So 3 is smaller than 9. So you remember that, set it to 3, and you take that action of going to the right. Likewise, here, if we go to the left, that's 1 plus 3 is 4. If we go to the right, that's 1 plus 4 is 5. In that case, well, 4 is less than 5, so we're going to go to the left. And so in each case, eventually we converge, updating this H of S. In this case, 1 plus 9 is 10, 1 plus 4 is 5, so we go to the right and we write a 5. Here it's 4, 1 plus 5 is 6, 1 plus 4 is 5, and we go to the right. And so we're using what we have from this H of S, taking our walks instead of a random walk, we're using that to influence our decision about which the fruitful direction to pursue. Does that make sense? Any questions? And it takes time to have this information. The more states you visit, this information you can think of as sort of washes over the state space. And with enough iterations, you'll fill in eventually reaching your goal. And so this is called learning real-time A star, or I said, I reverse the digits, LRTA. And this is the algorithm for LRTA. You start out, you do a goal check, and then if you encounter a new state that's not filled in your memory, then you're going to go ahead and you're going to update with your best path estimate from that state S prime to the goal. So then, if you're not stopped, you're in a real state, you go ahead and you update your results data structure. Again, that tells you how the environment transitions. Okay. So then you're going to do 2 things. You're going to fill in your H of S looking at the minimum cost action, and you're going to then return that action that minimizes that cost. So you're recording that action, and then you're returning the best action. And then you make that transition. Now your state and consideration is S prime and no longer S. So you keep doing that. And along the way, when you compute this LRTA cost, you're just adding the step cost to the estimate of what that successor state is that we just showed you in the previous slide for our visualization. And so over time, what happens is you fill in your understanding results of how the environment behaves, and then you're updating these H values using what you know about the successors to your left and right in this case. Does that make sense? Any questions? No? All right. And so this idea of learning and memory, you add a memory and this memory persists as you're exploring the environment. In some cases, you're just doing a random walk and you're filling in your understanding about how the environment acts back as you interact in the world. In other cases, you're using an effective propagation of this path cost estimate, and you're using that to influence your decision, which is improvement on random walk. In either case, as you interact in the environment, you get a new percept, the environment changes, you get a percept, the environment changes through your actions. And those changes could be because of things that you did, or it could be things ambient in the environment that are just changing, right? And so when we pivot to adversarial search on Thursday, we'll look at considerations for how you search in that type of environment. Because sometimes it's better to think about active agents in the environment that are not you, that are acting to maximize their objective and or achieve their goal. Other cases, you fold those other agents into the environment and just say, this is a weird environment that just changes in ways that are non-deterministic. But nonetheless, you perform some exploration. You randomly select actions, and those explorations are going to give you pieces of information that you then record and use to influence your future actions. So you get your percepts, you have some sort of memory, and we call this a learning agent. The learning agent uses something over the memory accumulated to influence the actions, i.e. the experience that it sees over time. Now, this experience can be many things. It can be static values. It could be proposals on, alternative pathways through the state space. It can be all sorts of things. There's no one way to have learning implemented through a memory. But at this first approximation, we'll just take this model from LRTA, star search, where we're just going to take our memory and we're effectively using that to propagate around the state space or representation of the state space, what this best path cost estimate does, and use that to influence what our next decision is. But the thing to remember is that we don't have access to the full state space like we did in Pac-Man search. All we have access to is our current state and the immediate successors for some definition of immediate successor. And through doing this random walk, we only have what we stored in memory, our own experience. And so if you had a large problem, you might choose to have an exploration step where your goal is to uncover new pieces of information or maybe explore different regions of the state space. And then after you get that experience, you might use it in subsequent rounds to try to influence the actions that you take. Does that make sense? All right, any questions? No? All right. So that's all I had to say. We have about 5 minutes left. We can always get out early. So with that, we'll pick back up on Thursday and we'll pivot to adversarial environments and models and considerations for that, which is in support of project number 3 on Pangolin. Okay? All right, so I'll see you all on Thursday. Have a great rest of the part of your week. Okay.